Hi guys, welcome back. In this video, we're going to discuss limits and their definition, and we'll look at one problem in three ways: numerically, graphically, and algebraically. Okay, so limits defined. So here's some notation. We have the limit as x approaches c of f of x equals L. That's how we say that. So let me write it down. The limit as x approaches c of f of x equals L. And what that means is, as x gets arbitrarily close to c, y equals f of x gets arbitrarily close to L. And if you're saying, what do you mean by arbitrarily close? We're going to talk about that. Sorry, we're having problems with the focusing on the camera there. Oops. Now, in general, you're going to know what this function is. You're going to know what C is. You're going to know what L is. And I want you to focus on this as two different quantities. On the left-hand side, we're taking the limit of a particular function as x approaches a particular value. And we're saying that that limit is equal to this number. And we just figured that out by reading the graph most of the time. We're looking for the y value that the function gets arbitrarily close to as x gets arbitrarily close to this particular number here. So here's an example. Let's say I say that the limit as x approaches 2 of f of x equals 5. A function that might look like that is this. So I go to x equals 2, y equals 5. And I want you to notice that as x gets close to 2 from the left-hand side and the right-hand side, oops, it's not the right color. The y values on the graph get arbitrarily close to L. So we would write the limit as x approaches 2 of f of x equals 5. Now here's another one. I have the limit as x approaches 2 of f of x equals 3. We might have a graph that looks like this. So maybe this is y equals f of x. Notice that as x gets close to 2 from the left-hand side and the right-hand side, the y values get arbitrarily close to 3. Now there is a difference between these two functions. In this function, that point x equals 2, y equals 5 is actually on the graph of the function. So we say that the function is continuous there. In this graph, the point x equals 2, y equals 3 is not on the graph of the function. We've got this open circle, which represents sort of a hole or a gap in the graph of the function itself. But either way, when we're taking the limit as x approaches 2 of a function, what we're looking for is what the y's get arbitrarily close to. We actually don't care too much about what happens at x equals 2 when we're talking about limits. We do care when we're talking about continuity, but in the case when we're discussing just the limit of the function, our concern is what the y values get arbitrarily close to as we get arbitrarily close to that particular value. So let's look at a graph and practice that idea.
Everything happens between you and Mustafa needs to be documented.
Okay, now this graph is definitely not to scale. All right, so let's say we're interested in this point right here. So maybe you've got this graph and you're given a problem statement, and the problem says, compute the limit as x approaches 2 of the function f of x, where y equals f of x is shown in the graph. Well, we compute or estimate the function's limit graphically by looking at the y values on the graph as x gets close to 2 from the left and from the right. So we look at the limit from the left, and we look at the limit from the right, and we say, well, what are the y values approaching? Well, as x gets close to 2 from the left-hand side, the y values approach 4. And as x gets close to 2 from the right-hand side, the y values approach 4. So this limit is equal to 4. Now we might also be interested in maybe this location as well. So I'll take the limit as x approaches 6 of f of x. Now to figure that out, again, I just look at the y values on the graph as x approaches 6 from the left and from the right. So as x approaches 6 from the left, and as x approaches 6 from the right, we look at the graph and we see that the y values are getting close to the x-axis, right? And on the x-axis, y is equal to 0. So the limit as x approaches 6 of f of x here is equal to 0. Now, if we were asked about this point, we're going to have a little bit of trouble. So let's say we have the limit as x approaches 5 of f of x. And again, I'm asking myself, as x gets close to 5, what do the y values get close to? And I need the y values to get arbitrarily close to that location. Well, again, I have to examine things from the left and the right of 5. As x gets close to 5 from the left-hand side, the y values approach this y value, which is y equals 3. But then if I look at the limit as x approaches 5 of f of x from the right-hand side, well, what do the y values approach from the right-hand side? Well, the y values approach 1 there. Now you can't have both of those two values. So in general, the limit as x approaches 5 of this function does not exist, and we abbreviate that with DNE. Now, both of these can't be right, so we've got to modify this a little bit. We said this is the limit as x approaches 5 from the left-hand side. If we're talking about the limit from the left-hand side only, put a little minus sign there. That means we're approaching 5 from the left. Now, this notation means the limit as x approaches 5 from the left of f of x is equal to 3. And then over here, we're approaching from the right, so we put a little plus sign as a superscript. This says the limit as x approaches 5 from the right of f of x equals 1. So that's the definition of a limit intuitively. This is the idea. And what we'll do if we're finding limits graphically or estimating limits graphically is we really just look at the graph and we look at what happens to the y values as we approach that value from the left and from the right. If they're the same, the limit exists and it's equal to that value. And if the limits are different from the left and the right, like in the x equals 5 example, we say that the limit does not exist in that case. So that's what we've got. All right, so now let's look at another problem, but in 3 different ways. Let's say we're interested in the limit as x approaches 2 of x squared plus x minus 6 divided by x minus 2. Now, if I know what the graph of that function looks like, I can just look at the graph, examine the graph, and think about what happens to the y values as x approaches 2 from the left-hand side and the right-hand side. If those limits are the same, then we know what that limit is. So let's look at that on Desmos.com. Okay, so this is our function y equals x squared plus x minus 6, all divided by the quantity x minus 2. And this is what it looks like. Now, in order to graph this, I had to define the function this way, and I also had to label that point, x equals 2, y equals 5. I knew that in advance, but you'll be able to label that point as well once we discuss how to solve this in general. But let's say you were just asked to find the limit of this function as x approaches 2. You can see down here on the x-axis, here's x equals 0, x equals 1, x equals 2, and then we would go up to the y values, and we would say to ourselves, okay, well, what is y approaching? Well, as x approaches 2 from the left, the y values are approaching 5, and as x approaches 2 from the right, the y values are approaching 5. So the limit as x approaches 2 of this particular function is equal to 5. Now I'm going to write that on my paper. Actually, I'll show you my paper in a minute. Now we can also find this limit at what's called numerically. We know that we can't plug in x equals 2. If we could plug in x equals 2, we would just plug it in, and that would probably give us the right value. And we'll talk more about those types of functions in a bit. But if I plug in x equals 2 to this function, I get x squared, or 2 squared, which is 4, 2 squared, which is 4, plus 2 is 6, and 6 minus 6 is 0. So I end up with a 0 in the numerator, and of course 2 minus 2 is 0 as well, and a 0 in the denominator. So this is a 0 over 0 indeterminate form. And it might not be obvious to us just looking at the function what the answer is. But we know from the graph, as we were just looking at, that as x approaches 2 from the left and right, the y values are getting close to y equals 5. So we can write this, and this is estimated graphically. You might say, how can I find that numerically? Well, one thing that we could do in that case is make a table of values. So we could say, okay, let's list the x values that we're interested in and the corresponding y values, where y is equal to x squared plus x minus 6, all divided by x minus 2. Well, if I substitute in x equals 1.9 to this function, my y values would be 1.9 squared plus 1.9 minus 6, all divided by 1.9 minus 2. If we do that calculation, it turns out that we get 4.999, or excuse me, 4.9. And that calculation was actually done right here. I labeled my function f of x, and then I just evaluated f at 1.9, and Desmos.com was able to calculate that for me. I got 4.9. And then we would do the same thing at 1.99. So you do 1.99 squared plus 1.99 minus 6, all divided by 1.99 minus 2. Enter that into your calculator, use parentheses as necessary, and you'll get 4.99. And if you substitute in x equals 1.999, you're typing that into your calculator. Make sure you put parentheses there and there. Then divided by 1.999 minus 2. Close parentheses there and there. Hit enter. And you'll get 4.999. And you see that as x is getting closer to 2, and of course we're zooming in a lot. We've got 1.9, and then we got 1.99, and then 1.999. We're getting closer and closer to 2. Those y values seem to be approaching 5. And of course, this is not to scale. Something like that. Now, if we do the same thing on the other side of x equals 2, we get something very similar. And these numbers that I'm substituting in, they're just pretty standard numbers. We have a tendency to just sort of divide by 10 and sort of go like a tenth to the left and a tenth to the right to start, and then just get closer and closer and closer by a factor of 10 or 1/10 each time. So we got y equals x squared plus x minus 6, all divided by x minus 2. And if we evaluate that function at x equals 2.001, and of course you don't have to write this, but this is what you would type into your calculator. Turns out you get 5.001. And the same thing from this one. And you get 5.01 if you type that into your calculator. So we're approaching x equals 2 from the right this time. So at 2.1, our values are approximately 5.1. And then 2.01, we're really close, and 2.001, we're really close. And we can see that those y values seem to be approaching 5. As we approach from the left-hand side, the y's are getting very close to 5. Oops. And as we approach from the right-hand side, the y values are getting very close to 5. And of course, we can use a calculator for that. You can use desmos.com. We've labeled the function f of x. Used 1.9, 1.99, 1.999. And then I'm actually evaluating them in this order typically, because I'm trying to get closer and closer from the left and from the right. But when we enter the values in the table, we have a tendency to write the x values in order. So we would do 2.001, we get this value, 2.01, we get that value, 2.1, we get that value. And so the x value or the y values are a tiny bit less than 5 to the left of 2 and a tiny bit more than 5 to the right of 2. But we seem to be getting closer and closer to 5 from our numerical analysis. So this is an estimate. And I just typed all of the values into this table. And you can do that on desmos.com by just hitting this little plus sign and entering a table right here. And you might say, okay, well, couldn't we figure that out algebraically or analytically? We've got x squared plus x minus 6, all divided by x minus 2. And we know that if we substitute an x equals 2, we get a 0 over 0, which is an indeterminate form. Well, let's take a closer look at this function y equals f of x. That function y equals f of x turns out can be rewritten. If this function has a factor in common with this function, I might be able to simplify it. And this function does have a factor in common with this function. To figure that out, we would factor the numerator. So first times first is x squared, so I'll have an x there and an x there. And then there are two numbers here. I need those two numbers to have a product of the constant term, which is -6, and to have a sum of that middle coefficient, which is 1. Since the product is negative, that means one of my numbers is going to be positive, the other one's going to be negative, and I need the numbers to actually have a difference of 1. So 2 and 3 will work. In order for the sum to be +1, I need the 2 to be negative. -2 times 3 would be -6, and -2 plus 3 would be +1. So those are the two numbers that go here and here. And now we see why we have the 0 over 0 problem, because if we plug in x equals 2 here, we have a 0 times a 5. And then if we plug in x equals 2 in the denominator, we have a 0. So this is a 0 over 0 indeterminate form, but this function is very similar to another function, a very closely related function. So this function has a cousin, and that cousin is the function x plus 3. And those two functions are going to have the same limit. And this function is continuous at x equals 2. I can plug in x equals 2 to this function, whereas I couldn't plug in x equals 2 to that function. So I try to plug in x equals 2, I get a 0 over 0. Since I can't do that, I try to simplify it in some way. In this case, I can factor the numerator, and the numerator and denominator have a factor in common, so we reduce that common factor. And then we take the limit as x approaches 2 of this function, and we say, can we just plug in an x equals 2 here? And we can. When I plug in x equals 2, I get a limiting value of 5. Now, one of the things that I want you to notice is that we kept this limit notation the entire time until we were ready to plug in x equals 2. The beginning, if we plugged in x equals 2, we'd have a 0 over 0. We can't do that. But after simplification, we see that the limit of this function is equal to the limit of this function. And this function is what we call continuous at 2, meaning it's well-defined at 2. You can plug in 2 and you get out an answer. When we plug in 2, we get a 5. And so that's the value of our function. Or excuse me, the value of our limit, the limit of the function. So let's graph that now. I had the function f of x equals x squared plus x minus 6 divided by x minus 2. And we said that that's the same as this function. And provided that x is not equal to 2, that's the same as x equals, or x plus 3. So you have to add that restriction. So if I want to graph the function now, I just graphed the line y equals x plus 3. That is a y-intercept of 3 and a slope of 1. But f of x doesn't look like this line. This is the closely related function. F of x looks like this. F of x is equal to x plus 3 as long as x is not equal to 2. So at x equals 2, we've got an open circle there at x equals 5. And f of x looks like this. So the two functions have almost identical graphs, except f has the hole in it at x equals 2, y equals 5. Whereas this other function, y equals x plus 3, is just a solid line. So let's summarize what we just talked about. So we can estimate or compute a limit in 3 ways. Now, if we know what the graph looks like, we can just look at the graph and think about what happens to the y values as x gets arbitrarily close to a particular value. So we looked at this as x approaches 2 from the left and from the right, and we said the y values approach 5. So you can compute a limit graphically. You can also compute limits numerically. Of course, this is an estimate. Sometimes your calculator will give you the wrong answer, but you can sort of sense trends by substituting in values close to the x value that you're interested in. So for this problem, we were interested in x equals 2, just because it was given to us. The limit as x approaches 2 of this function. And we just said, okay, well, if I plug in x equals 2 to this function, I get a 0 over 0. But what happens if I plug in values that are close to 2 from the left and from the right? As x gets close to 2 from the left, what happens? And what happens to the function as x gets close to 2 from the right? Well, when we do that, we substitute those values into this function. We get 4.9, 4.99, 4.99. So as we approach x equals 2 from the left, we get y values that are getting very, very close to 5, but they're a little bit less than 5. And look, that's consistent with our picture. And then as x approaches 2 from the right, we've got that 5.1, 5.01, and 5.001. We see the y values are getting very close to 5, just like we have on the graph here, but they're a little bit larger than 5. So this numerical analysis seems to imply that the limit is 5. Now, another way you could do it is you could just simplify that function to begin with, and we could say this is equal to this function, as long as x is not equal to 2, and then the computation is even easier. Just take 2.001 and add 3, you get 5.001. Take 2.01 and add 3, you get 5.01, and so on. Those functions are exactly the same, except with this function you can't plug in 2, with this function you can plug in 2. When you plug in 2 to this, you get x equals 5. When you substitute in 2 to this, you can't get x equals 5, but you see that the y values are getting arbitrarily close to 5. So that's examining a limit numerically. And then finally, limits algebraically or analytically involves not really looking at the graph, but thinking about that expression there. Now, all 3 of these methods tell the same story. If I think about this expression and I say, okay, I can't plug in 2 because I get a 0 over 0. Is there any way I can get rid of the 0 over 0 problem? Well, I can simplify by factoring and then reducing a common factor. Like that's the limit algebraically part of this. But I want you to remember that this is saying the same thing as this over here. This just says that the limit of f of x is equal to the limit of that function, that linear function that doesn't have the hole in it. And you can just plug in x equals 2 there to get the value. If you look at it numerically, the numerical method tells the same story. And then, of course, the graph tells that story as well. But they're just 3 different ways of doing exactly the same thing. So that's limits. Next time, we're going to talk about 3 ways that limits fail to exist? We've already talked about one of them. So you might have different limits from the left and the right. The different limits from the left and the right of some value. And of course, we're talking about different limits of a particular function f of x. And then we'll do the same, and we'll look at two other ways that limits can fail to exist. And I'll just outline that for you. If the function exhibits unbounded behavior, the limit fails to exist in a particular way. And if the function oscillates rapidly between more than one value, then the limit would fail to exist. But that'll be in our next video.